Welcome. Good morning, good afternoon to everyone out there. My name is Chris Doran. I am a technical sales specialist for Global Test Supply. Thank you for joining us for our webinar today via Global Test Supply University. Today's topic is temperature calibrations, drive improvement with practical solutions. Throughout the presentation, we ask you to kindly mute your microphone. Presentation will be between 40 and 50 minutes, and we'll have a little bit of time allotted for Q&A at the end of the presentation. We are going to encourage you to use the chat feature throughout the presentation to submit any and all questions that you may have. It's great to have an expert like Ken with us today, so please don't be shy. Get them all into the chat feature throughout the presentation. So Global Test Supply has been working with Fluke for many years. We pride ourselves on being a leading distributor. This is a result of our dedication to offering you our product expertise, service, and competitive pricing. Today's webinar is presented by Ken Reeves. Ken is Fluke's territory sales rep based in Alberta, Canada. He has 31 years of technical test equipment sales, which include over 20 years working directly for Fluke. Ken, I will turn the presentation over to you, and just a quick note. Typically, we would have a webcam, although we are experiencing a little bit of technical difficulties today, so it'll just be myself on the webcam and Ken will be presenting. So Ken, over to you.
Thank you very much, Chris. And I'll apologize right off the gate that I don't have my webcam running properly. Today, I want to take the better part of the hour here and have a quick discussion with regards to temperature calibrations. The presentation today, the title on it is Driving Improvements to Your Calibrations with Practical Solutions. But in reality, the goals of what we'd like to cover today is give you some information, not only what is calibration, but pass on some knowledge that we have in terms of how to make improvements to temperature calibrations, either through some of the knowledge we're imparting or some of the tips and tricks, and maybe even some best practices. So without any further ado, we got a lot of content to cover, and we will be finished hopefully within 40-45 minutes. So let's review temperature calibration, or calibration in general. It's a good place to start. Calibration, just as a review, is where you take a known standard and compare it to an unknown standard, an unknown value. So the known standard is typically more accurate. Industry likes to see 4 to 10 times more accuracy in your known standard and comparing it to an unknown standard. So in this particular case, we got a picture of a Fluke guy using a Fluke 754. It would be 4 to 10 times more accurate than the device that he's calibrating in this box. And I'm not sure what that is, but that's kind of an industry reference and standard. You may hear the word traceability tossed around a little bit. I want to just give you an idea what that means from my perspective. Traceability is really not a whole lot more than the actual documented paper connection between the country standard or the SI unit standards all the way down through the secondary standards that you might find at GTS's labs into working standards that you take out in the field, like this 754. Down to your process instruments, and your part in that traceability chain is doing the documentation stage between taking your standard into the process field. Traceability unto itself doesn't necessarily guarantee accuracy. There'll be more of a discussion about that further, but traceability is just the concept that everything my process has seen has a connection all the way back to a country standard. Let's review SI. SI actually stands for International System of Units. SI is French, so they swap the words around. And in this particular case, the SI unit for temperature is actually Kelvin. It takes you back to, maybe some technical training you had at some point in time, or even back to maybe high school. But Kelvin is a temperature scale that's closely related, actually it's directly related to degrees centigrade. Degrees Fahrenheit is a different scale, but they're all primarily referenced back to the Kelvin. Kelvin starts at 0 Kelvin, which is considered absolute zero. You can't have a negative Kelvin value. And absolute zero in centigrade is minus 273.15 degrees Celsius. 0 Celsius, which is kind of the reference point for the zero point on the temperature scale for Celsius, is actually 273.15 degrees Kelvin. Now, what they determined or what they discovered is Kelvin is actually an energy type temperature measurement. Temperature is energy, I guess is a good way to word it. The energy of a particular system or the temperature of that system has to do how much kinetic activity there's happening, how fast those molecules are moving. And going back to some of the thermodynamic laws that we won't get into heavy detail here, but the idea is that the faster they move, the more temperature they have. So even at 1 degree Kelvin, you do have some energy, and even though that's really, really cold, you still have some energy. The standards, again, for what we would deal with primarily out in the process industry or in your particular place of operation will be either referenced to degrees Celsius or degrees Fahrenheit. And we don't deal in Kelvin too much unless you get higher up into the standards chain and get up into those country units, which again, SI is the standard, Kelvin is the standard at SI. So why is temperature important? Temperature is everywhere. As humans, we experience it. We use temperature to our advantage. We manipulate the temperature of certain materials to achieve certain results. I was just on the phone recently with a customer that needed to get a precess steel to somewhere between 400 to 500 degrees Celsius before they did their welding. And so those are the kind of things where we need to get temperature and use it to our advantage. In the process industry, you can have specific reactions or specific types of known events happen at a given temperature. And if it's not at that temperature or it's more than that temperature, you may get unexpected or undesirable results. So ultimately what it means is we have to be able to not only measure, but send that signal information back to control systems, and then a part of that whole process is calibrating them so that we know that every piece of that system is correct. So I don't know if you know how to do a screen grab on your computer. You might want to just get close to get ready to how to do that. We will have a page coming up here talking about kind of a checklist for your workload. But before we get to that point, I wanted just to do a quick review of what a process loop is. So a process loop, in this case here, we have a process fluid. Let's just call it a tank of water. And this tank of water is getting warmer. There's heat being applied to it. There's a temperature element, sensing element that we can't see. It's in here, and it's actually in contact with the process fluid. That temperature sensing element will send some sort of temperature sensing or temperature measurement parameter back to a transmitter. The transmitter will convert this temperature sensor value into a 4 to 20. There's your loop that we talk about, the 4 to 20 milliamp loop, back to a indicator or controller or whatever the case may be. So right now we see that the process loop coming back to the controller is indicating that it's measuring the temperature of this fluid at 97.4 degrees Celsius, and that's right there on the end of the sensor in contact with the fluid. What'll happen is we're applying heat, so it's going to get warmer, and eventually it'll get warmer. And the question is, does it actually achieve the temperature we're shooting for? Let's assume we want to get to 100 degrees Celsius. The answer is yes, we've achieved that temperature. Then the controller itself will send a signal down to a control valve. And in this case, the valve was open. It will tell the valve to turn off, and it'll shut off the fuel going to the burners. And that's when everything's all satisfied. So very simply, a control loop will go this way. When the temperature starts to drop off, it'll say, no, it's not achieved, and it will turn the valve back on and ignite the burner and reheat the fuel for us, sorry, reheat the water for us. And again, that's just a very simple rudimentary example of what a process loop is. The reason I'm taking the time to show you about the process loop is we're going to talk about how to calibrate this sensor, how to calibrate the transmitter, and how to make improvements on this part right here of the whole process calibration. I mentioned earlier about your screen grab. If you have that capability, now would be the time to do it. I'm not going to run through every single point here, but when you go to make sure that you have the right pieces of test equipment to do your calibrations, these are some questions that you might want to ask yourself. So first of all, what are the temperatures that we need to calibrate? Maybe not just the specific temperature of that application, but what does our entire operation at our company look like? Do we have any very high temperatures that we need to calibrate? Do we have any very low temperatures that we need to calibrate? What are the accuracies that we'll be satisfied with within our process loops themselves? Do we need tight tolerances on our process loops so that we're happy with 1 degree, or are we happy with 4 or 5 degrees Fahrenheit as a process loop calibration? Do we have any critical pieces of accuracies that we need to maybe go and look for specialized equipment to do that particular calibration? And you can run through here. We'll talk about sensors and switches, and then if you have HeartSmart transmitters, and do you plan to take the calibrations from the field back to the lab, or do you want to do them in the field where it's easier to just leave them in situ, as we call it? When you take all of these things that are listed here into consideration, you will wind up getting a better scope of what your overall workload looks like. And when you understand your workload, you can compare that to your test equipment that you're going to bring to that workload and be assured that you've got all your bases covered. And having that equipment available to yourself that's calibrated, traceable, ready to go will make your life just that much easier. So as I mentioned, temperature is everywhere. It's actually the second most measured variable in the world. Just ask yourself what the first might be. And if you haven't come up with it already, the first measured variable is time and the second is temperature. Understanding the differences between how we measure these temperatures and what types of considerations we have to put into place. And again, in addition to the previous list, you may need to know some of these other points between, say, sourcing and simulating. This will be the context of what we're going to continue the conversation on. So, what devices do you need to calibrate? You may have some physical contact type devices out there, things such as liquid and glass thermometers, bimetal gauges, expansion temperature gauges that might be liquid filled. You may have some gas actuated temperature gauges. These are actually mechanical type devices. They may most likely do not send any kind of signal out. They have just visual indication. And then if you're using probes to make your temperature measurements, you'll find that you have probably a lot of thermocouples in your system. You may actually have some RTDs if you're looking for maybe more accuracy. We'll talk about what that looks like. And if even more accuracy or you want tighter controls, you can use thermistors. Those are the types of physical unique electrical signal outputs that are available from different probes. So the advantage of using a contact type probe is that the probe is actually in contact with the material itself being measured. Therefore, there's an assumption that the probe and the material are the same temperature. Having a contact probe will cover a wide range of applications. And if it's a visual indication, a mechanical type probe, you don't actually need power there to get an idea what the temperature is. You can get that temperature measurement without the power being applied to it. So if you have a bimetal temperature gauge, you can just walk up and do a local indication and say, yep, that water temperature is 97.4 degrees Celsius because I see it on the gauge. If you have a long distance to cover, this is where transmitters come into play. Transmitters are exactly that. They take a sensor measurement element value and convert it into an industry standard 4 to 20 milliamps, or maybe even some kind of bus configuration where we can send that signal digitally back to a control plant. The decision making may not be just as simple as what's happening in this loop. There may be other variables involved, and that's where a control system will come into play, make those decisions based on a bunch of different parameters, and then send process signals back through the loop out to the devices that are under control, like that valve in the previous example. Being able to measure all of these different parts is critical, and that's really what this entire presentation is going to be about. Just a quick comment between RTDs and thermocouples. So I mentioned them earlier as the most potentially the most popular versions of temperature probes that are out in industry. If you're not familiar with the differences, thermocouples themselves are fairly inexpensive. They're actually made with two dissimilar metals that are fused together, and those dissimilar metals will create a kind of a standard millivolt output based on what the temperature of that junction is called. So where we fuse them together, it's called a junction, okay? The thermocouples themselves can be very inexpensive. They're like typically a third of the price of buying an RTD. They have a wider temperature range than RTDs. You can get thermocouples that get you into the 2,500 degrees Fahrenheit, which is, I have to do some math, but several thousands of degrees Celsius and Fahrenheit. So very, very high temperatures. The big thing about a thermocouple compared to an RTD is the RTDs are more accurate. The reason is that the temperature output, sorry, the resistance output based on temperature is greater for an RTD than the millivolt output of a thermocouple. So that gives us more signal to deal with. And when we have more signal, we can get more granular and therefore more accurate as to what the actual temperature value is. So you'll find that RTDs are sometimes typically 10 times more accurate than a thermocouple itself. So you can get a 1/10 of a degree pretty easy with an RTD, where you would have to, be comfortable with a 1 degree on a thermocouple. The temperature response times on thermocouples much faster than RTDs. RTDs are resistance temperature devices, and the material itself needs to change that temperature, where you have just a single point of temperature changing at that junction on a thermocouple, and it's much faster. Another comment quickly, let's skip down to stability and repeatability. So stability is the ability of the probe to remain at a temperature without moving around. Repeatability is where, say for instance, the probe read 97.4 degrees Celsius, and it cooled off and it came back up and went to 97.4 degrees Celsius, so it was repeatable at that same point. Thermocouples can drift over time because of the chemical changes in the sensor material, and RTDs have a tendency to be more stable over time. So that's just the takeaway between the two different systems. There is a very popular method for making temperature measurements using non-contact temperature measurement tools. So those may be, they go by so many different names. They can be pyrometers, temperature guns, spot radiometers, heat guns, whatever version that you call it, it's not wrong. It's pretty much the same thing. What you need to understand here is we're not actually making contact with that process fluid. So in the previous example of that loop, we're not measuring the water, we're measuring the temp. If we were using a temp gun, we would be measuring the surface of the tank that's containing the water. And we're not actually measuring the temperature, and take it a step further, we're measuring the infrared energy coming off of that surface. So there's a lot of assumptions that can happen with a temperature gun. That combined with the fact that most temperature guns are typically plus or minus 2%, they don't turn into calibration tools. Although they get maybe misapplied or used as a reference. We have some people, like we have temp guns that have a laser on them, and some people think the laser makes the temperature measurement, when in reality it's measuring infrared energy at a spot given over a distance, and we call that the distance to spot ratio. We could have a complete discussion. It might even take another hour-long session, and we may come up with another university version of this, where we have a complete discussion about infrared energy and how to make improvements on and making those temperature measurements. Just be known that these are out there, they're very popular, and they do a great job of temperature comparison, but actual temperature accuracy, there is a lot of room for understanding and improvements to be made there as well. There are some advantages to non-contact. So if something's electrically live, I don't expect you to put a probe on that and make a measurement. If something's moving or rotating, I don't expect you to do that. If it's too far away, up in this example here, you're trying to measure the surface of a temperature in a pipe, and it's significantly 30, 40 feet, you'd have to climb the ladder, put the probe on there. Maybe it's easier just to take a temperature gun and measure the value. So there's a lot of advantages, and prices have come down to the point that you can get a pocket thermal imager today, one of the PTI 120s from Fluke, and get an image similar to the one in the bottom corner here and spend less than $1,000 very easily. Let's get back to actual probe calibrations and temperature calibrations. So right out of the gate, you have a decision to make. Do I want to include the probe as a part of my loop calibration, or do I want to calibrate the probe separately and then simulate that value from what the probe would be into the process? So let's talk quickly about what simulation is. So simulation is the term that we use where we pretend to be the probe and we send a signal into the transmitter. The signal value in this particular case is shown as 50 degrees Celsius. We send what would be the millivolt value off of the table into the transmitter. The transmitter responds and gives us a 4 to 20 milliamp signal that's corresponding to the way the transmitter was programmed. Okay. When we have a simulator like a Fluke process, this one's a 724 temperature calibrator. When we have one of these tools available to us, they're small, easy, battery-powered devices. They carry RTDs, thermocouples, millivolt values, resistance values. You can do temperatures in degrees Celsius and Fahrenheit. There's a lot of things that can be programmed into them. But ultimately, at the end of the day, the device itself provides a thermocouple value and accurately measures the 4 to 20 milliamps back. Now, what we're doing here compared to the loop is we're actually not measuring what the sensor itself is doing. We're assuming that the sensor is what it is either in or out. We have no way of confirming the sensor. We can do a comparison calibration, which I will talk on here a little bit later, but that's when you would use this device to measure the thermocouple value off of your thermocouple in the process, and then have a secondary probe somehow measure the process at the same time and be able to compare the two. Okay. When do you go consider a simulator? It's when your system accuracy allows the probe simulation back into the process. So if you have plus or minus, 2 or 3 degrees loop calibration and you're happy with that, this is a perfect application. If you're not able to remove the probe from your process without creating disruptions, so if removing that probe would mean that you'd have to shut down the line, that would be kind of ineffective because you wouldn't be able to measure that temperature anymore. But if there was a disruption, then you have to leave the probe in service. That's just the way it'll be. Tests that require quick calibrations rather than physical temperature sourcing can be provided. So we'll talk more about the time difference between simulating and sourcing. Simulating is literally minutes, and sourcing can be, to do a proper full calibration could take several minutes. We're talking maybe in the order of a half hour or longer. You may also be limited physically. You have some tight spaces or tough access or safety concerns. And using a simulator in that example would be much easier than trying to turn on a sourcing device, such as the next page, a dry block. So sourcing is when we actually provide the real temperature, the real exact temperature to a temperature measurement probe. And that probe is typically tied into a transmitter and sending the signal. So we're doing it all at once. The actual physical temperature is what we get when we use like a dry block or some other source like a wet bath, okay? You can consider using a physical source to do this when you want to eliminate the actual error from the temperature sensor itself during your calibration. If you have the ability to remove the sensor from the process, you have the sensor itself might be in a thermal well. You'd be able to take it out of the process. The well is maintaining the integrity on the process line. Take your probe out of there, drop it into the dry block, do the complete system calibration where you source temperature into that probe, measure the corresponding response from the transmitter, and then you take your probe back out knowing that the whole system is calibrated and slide it back into the process. Another thing you might want to consider is doing the probe independently if you need to linearize the probe. We can talk more about what that is a little bit further in this discussion, but we'll touch on something called calendar Van Duzens. That's where you know exactly what the resistance outputs are at the probes and basically create linearization to standardize the probe. It's a significant improvement, and you'll see a table on that a little bit later. And if you need more accuracy than the readout would provide, this is the readout on the display. We've just taken this image behind here and shown it up front, and that's what it's doing. Is it's measuring this internal standard sensor inside and saying this is the temperature I'm trying to achieve and heating the elements. It's its own little process loop here. But if you need more accuracy than what this probe and loop combination can do, you can insert a secondary probe directly beside this probe if your well has room for it. We'll talk more about that separately because it's a discussion for eliminating errors. All right, things to know when you're calibrating a probe. What is the temperature of the probe, or what is the temperature of the process that I need to simulate? what is the shape or the diameter and the length of the probe? Is it an irregular shape, or is it a nice, consistent 1/4 inch, 12-inch long probe, or is it a temperature bulb that has irregular shapes that, I can't necessarily put into a dry block? Where is the sensing element in that probe that you want to calibrate? Is it at the tip? Is it in the middle? Do you have 2 or 3 sensors in there? It's important to know that information when you come to picking and choosing the proper calibration source. In other words, the dry block or the dry well. And do you need to calibrate more than one sensor at a time? And what we mean by that is if you're doing batch calibrations and you're a thermocouple manufacturer and you would like to calibrate 100 probes at one time or confirm the accuracy of 100 probes at one time, doing those in a single hole drywall might take you a very long time. But if you did them all at once as a batch in a fluid bath, that might be a better approach. We do want to bring to your attention that there's something out there called a micro bath, and I got this little picture over here. These are lab grade baths. They typically sit on a bench or have their own cart in this case, and there's lots of fluid, and that's the kind of application where you're doing batch type calibrations. I don't expect to see these in places other than lab type environments. They would be a couple of steps above the accuracy you would need for process calibration typically, unless you're doing pharmaceutical or something that requires more accuracy. But there is a portable version. It has a screw lid on the top here. You can unscrew the lid, and this allows you to do odd shape or regular sensors in the field. And they're very popular. They're quick compared to these ones. These ones take, hours to stabilize. This one here takes minutes to stabilize. So just be aware that they're out there so you're not force fitting probes into applications that were not intended for a dry block. Okay, let's talk quickly about dry blocks themselves. So first of all, today's dry blocks, they are, I call them lightweight. For the most part, a dry block calibrator is 20 pounds or less. If it gets to be more than that, there's a handle on board. But the biggest advantage is that they're super fast and they're portable. So in the past, you used to have to take probes and bring them back to a lab type environment. Now you can take, as long as you have 120 volt outlets available, you can plug these in and do your temperature calibrations in the field, okay? We'll talk more about this next bullet further on in the slide, but we have an ability to calibrate do automated calibrations using a Fluke 754 or 744 documenting calibrator. And that will free up a ton of time. We'll talk about that independently. Dry blocks are very, very popular. Getting back to that workload discussion, if you had a really good understanding of the different types of probes that you had to calibrate, you can pick and choose appropriate inserts for the different models that we have available. So we have some models that have multiple holes that are all the same, or we have other models that have different size holes for different applications. But these inserts are exactly that. They can be inserted into the block and then take it back out again and insert the correct well into the block. So effectively, you're changing what the capabilities of the dry block is by just changing out the insert, okay? We have some models that can actually run what we call cold calibrations, so below ambient or sub-ambient temperatures. They do not only temperature heating, but they also have cooling effect capabilities in them. We cool them using Peltier thermocouples, which is the same technology you have when you have one of those plug-in coolers that you run in your, in the summertime when you want to go camping and keep your pop cooled or whatever the case may be. You can plug this into your 12 volt outlet in your vehicle and it will cool things down. We use the same technology, obviously to an industrial level and accurate to the standards that we need, but we were able to pull the blocks down below ambient. What else is there that we need to talk about? Comparing themselves directly to baths, there's some pretty obvious differences. A lot of times the fluids that are used in baths can be silicone fluids. They are prone to potential contamination. They also might off gas, so you need to have fume hoods installed. This is the type of lab type equipment that typically doesn't see the field. So that's where a dry block comes into play. Alrighty. I mentioned earlier about a comparison calibration. This is where if you have the ability to, you can't take this probe out of service or you'll break the integrity of the system. if you have a well or some other place where you can just walk up and slide in a probe and basically simultaneously measure a single point between two probes, then you have the ability to take something that's more accurate than your process device and do a comparison calibration. This is a very popular product from us. It's called we call it a temp stick. That's probably what most people would call it. They may not even know the part number is 1551A, but it's an RTD accurate temp stick that can slide into the process. And, again, getting back that RTDs are typically 10 times more accurate than a thermocouple. It's a quick, easy way to do a quick comparison on thermocouple measurements. We have an even more accurate version of this. So if you're involved with liquid flow calibrations and you need to know the exact temperature of the liquid because it maybe changes density significantly as a part of your calculations, we use these types of devices in those applications all the time. They're a step more accurate than this. I do want to point out something really quick here. We're going to talk about something called stem conduction. And this is an example where perhaps this person is using this probe and it's accurate enough for them, but there is significant errors with the heat or whatever's in here conducting up the stem and radiating away and being a source of cooling to the actual process. But we'll talk more about that later. Again, if you have any questions on what I'm talking about, please use the chat window and we'll address them here at the end. Alrighty, I mentioned earlier that non-contact calibrations and non-contact temperature measurement devices could be a completely separate 1 hour session. So I will not spend a lot of time on this slide, but I did want to bring to your attention that we do actually have temperature sources that will work with temp guns. So I don't know if you have a grocery store nearby and you see these folks walking around with their temp guns that they go out and check the coolers to make sure that the meat in the cooler is still running at a certain temperature. It's kept cold so that it meets HACCP requirements or whatever the case may be. But you heard me mention earlier that they're plus or minus 2% accurate or 2 degrees Celsius accuracies. There may be some concerns there that, well, is that really the right thing that they should be doing? So one of the things they can do is make a morning reference to a temperature standard in a non-contact format, and they can just quickly, point their temperature gun at the standard. It says it's 100 degrees Celsius. They point it at the standard, and their temperature gun says, well, actually it's 99.4. Then they know that when they go out and measure, they might be reading slightly lower than what would be happening in the actual cabinet. But that's a real quick, easy way to do calibrations and or verifications. Okay. In the sidebar, you will see a word says right above chats, at least on my screen, it says handouts 4. So there's 4 different handouts that are available, and one of them is a handout that you can get either from our handout in this window here, or you can write down this really nasty link that's in our software, in our presentation, but it takes us to a 26-page application note that Fluke has put together to help you improve your calibrations for all of these different categories here. So if you see any of these in the listing here that are exciting to you or interesting to you, say for instance, you're interested in looking at temperature switches and controllers on the bench or in the field, we have specific application notes kind of condensed into one 26-page document that'll help you make improvements. What we're doing for today is we're going to break out 3 of the more popular ones. And we're going to address them independently in this presentation today. So hopefully the ones that are exciting to you are here. So without any further ado, go get those handouts if you want them. In the meantime, take a look at the presentation here. We're going to talk about some best practices and tips. So when you need to calibrate and test the RTD itself, the one that's in the process, you typically need to have it connected to a source such as a dry well or a microbath. However, the problem is that the sensors are typically being calibrated in this well. And let's talk about some of the improvements. So typically RTDs are checked while they're connected to your device, such as a panel meter or a transmitter. However, if you suspect that the temperature sensor itself is out or there's a problem with the calibration, you need to perform the calibration on the RTD or the thermocouple, independently of the loop. So to do that, we actually have to source the temperature to that particular probe. And in doing so, that's where we use a dry well calibrator. So what we'll do is we will insert the probe in there and measure the actual output from the RTD itself, okay? So we'll measure resistance as an example and then compare that resistance to a table, or we will use something like a Fluke 712B or a 714B or one of our other multifunction or documenting calibrators that can take the actual raw thermocouple and RTD values in here and convert them into the actual degrees C or degrees F on the display. So these devices basically contain all of those lookup tables for you to measure them. And that's how you get your accuracy. And then if it's been calibrated, that's how you get your traceability. Okay, so getting your actual source values, this is where you have some critical measurement points that need to be confirmed. So typically an RTD is in process, and say for instance, a reaction happens at 75 degrees Fahrenheit. You will use that RTD and you need to confirm that that's actually happening. Then you can put it in a dry well that's going to give you 75 degrees Fahrenheit exactly at that point, and then compare the output to what it should be. Excuse me. So, and then we mentioned the different wells that you can use and pick and choosing. One thing I want to point out here is this fourth bullet down. So if you're using a dry block or a dry well calibrator, I highly recommend that you keep it dry. We have some people that will use oil on the side of an insert in an attempt to, create better thermal conduction. You don't need to do that. The folks at the factory and the engineering side of our company have spent a lot of time looking at the material expansion rates based on temperature and engineering in the air gaps that need to be done to be able to put a well into a dry block, heat it up, and then let it cool down and still be able to remove it during that process. So if you decide to put some fluid on there, that fluid could basically get sticky or coke off and then seize that well into your dry block. And now you have, at that point in time, you have two things that have happened. You can no longer change the well out. And if you needed to change the size, then you're stuck. You can't, like, literally stuck. And if you also have created a bit of a barrier between the two materials, that may not be a good thermal conductor. So you created like an insulating barrier in there, and that's a problem as well. Don't put fluid into a dry block in an attempt to turn it into a multi-odd shape type dry well. That's not recommended practice at all, because no matter how much you clean it, there'll still be something left over. And it's also potentially dangerous because a lot of dry blocks will get you much hotter than the actual fluid can maintain. So if you use water as an example, and our dry block goes to 200 degrees Celsius and water boils at 100, then yeah, you're gonna burn that water off. If you're using oils, even worse scenario, you can get some very, very dangerous temperatures happening with a dry block. So again, don't do that. A tech tip we can suggest is, because temperature sourcing takes a long time to heat up and stabilize and become, at the same temperature, and you have temperature uniformity between the probe that's in there and the sensor that we're using to control everything, maybe even a secondary probe. Once all that becomes stabilized, that may take the better part of, anywhere between 10 to 25 minutes. And if you had multiple temperatures to change, that's just adding time to your entire calibration, which is just a function of how things happen. But what we recommend is you start from your cold temperature and go to your hot temperature. The reason is that we have much better control at being able to bring that temperature up rather than just blowing a fan on everything and attempting to cool it back down using ambient air. So again, doing a calibration using a dry well, if you had 3 points of calibration, we would recommend you start at the colder 0% point, go to your 50% point, and then go to your 100% point. Let's talk quickly about linearization. There is a really good opportunity, if you have a temperature source already, or if you need to buy one from us, that you can run your well with a secondary probe. So your probe itself has your unit under test probe and your secondary probe simultaneously. And if your secondary probe can give you either the actual resistance value with enough accuracy or the Fahrenheit value with enough accuracy, you can get some pretty significant improvements in the accuracy of the dry well itself versus the sensor that's built in board to control the temperature and do the set point. So this can be, in many cases, this one here, this case here could be, easily 10 to 20, 30 times more accurate than the accuracy of the dry well itself. So what I'm saying here is that if we know the actual resistance output values of our test points, we can use this and go through some calculation in a software we have called Table View. And it gives us these type of improvements in the bottom of the presentation here. So you may be running with a Rosemont transmitter, that's their advertised specification. A standard RTD probe might have this accuracy, but if we go through the process of creating a polynomial that will linearize the probe, in other words, take this black accuracy curve and create it more closely to the ideal, that will give us improvements easily in the order of 5 times more improvement on the probe. And then the total system accuracy could be literally 4 times more accurate. So if you have a transmitter that has the ability to enter calendar Van Dusen probes, and you have a dry block and you want to calibrate your probes and make them more accurate and marry the probe with the transmitter using this polynomial equation, we have all the equipment to help you do that. I guess that's the final takeaway, is that if you need technical help doing this and you want to take advantage of that, you can just give us a call. Alrighty, let's talk and change gears and switch over to simulating modes. So simulating thermocouples and RTDs, probably the more popular way to go about doing things, again, because they're faster, a little bit quicker and easier. You get to see the numbers live. You're giving up a bit of accuracy for that speed, but there are some advantages. So let's talk about this and come up with a few ways that we can make some improvement to this part of the process. So here's just a quick example. You've got your thermocouple and it's connected directly to your transmitter, and again, reading 4 to 20 milliamps back. If you're using a thermocouple to simulate into the transmitter, be sure that this is the correct thermocouple end and thermocouple wire for this application. So if your transmitter is expecting a K-type thermocouple, make sure you're using K-type wire and K-type ends. If it's a different type of transmitter, make sure you change out the wire to the correct configuration. Another tech tip is don't try to extend your thermocouple leads with either different wire from a different thermocouple or just regular plain old Fluke test leads. In doing so, you actually create secondary junctions called cold junctions, and those junctions will actually, depending on the temperature of everything, could potentially subtract or add to the temperature measurement that's being used and creates inaccuracies. Another takeaway for RTDs is most RTDs are either done in 3-wire or 4-wire configurations. So know your configuration design of your transmitter, what your transmitter is expecting, and make sure that when you are simulating into the device that you're using the appropriate connections, so 3-wire or 4-wire. And doing so, don't jumper at the transmitter and then take a set of wires back. Use a full length of test lead of the same material. So don't mix and match your test leads, I guess is the takeaway, and use something simple like our stacking test lead jacks. And that gives you a single point into the device, but it allows you to terminate both very close to where the measurement is being made. The reason this is being done in the first place is we are actually taking a measurement between the probes and the wires and determining the resistance of this test lead and subtracting it from what's happening here to here. So effectively, we're eliminating or removing the test lead's resistance from the overall resistance being sourced into the transmitter. So again, very, very important to keep in mind. We see lots of different versions of this out in the field where people will, grab whatever test lead they can and use it, and or just quickly, take a jumper and go across and be done with it. And that would be an inappropriate way to make the measurement and effectively reduce the accuracy when you think you've got it already. Okay. Okay, let's take a moment and talk about automating the temperature calibrations. So one of the major advantages we have available to us is doing automation to do temperature calibrations. I mentioned earlier that it may take, let's say, 20 minutes to stabilize at a standard temperature, move it to the next temperature, another 20 minutes. And so therefore you've spent an hour doing a 3-point calibration, and you've had to basically babysit this the whole time you're there. So you're making the adjustments and writing the values down, but what do you do? Well, there's nothing to do. You know, maybe wait for the value, or catch up on your email, or whatever the case may be. What we have is a pretty unique solution. So if you own a Fluke 754, which is by far the most popular documenting calibrator out in the industry, and we sell thousands of these. If you have one of these and you own a Fluke or Hart Scientific, which is the company that we bought and is a part of our temperature calibration family, the metrology side, if you own one of these, there's a cable you can buy from us that will allow you to connect the two together. And what that allows you to do is do something that we call sourcing a dry well. And we can actually use the 754 to change the set points automatically on the dry well, and then measure the corresponding response and automatically document and capture that into the memory of the 754. So I'm going to show you a quick little version of what that looks like. So when you go and you select source of temperature, you got a choice between sourcing thermocouple, sourcing RTD, which are those electronic sources that we're used to. And then we also have the ability to source a dry well. And that dry well allows us to communicate with the device. And then once we find it, we can go in and do a setup and do an automated calibration where we say, what are we going to measure and what are we going to source for values? And now we can change up the test strategy. You can change up the test strategy to be maybe more points, or more points up and back down again. Either way, it's all completely automated. And at the end of the day, you get a bunch of results. You get what the sourced value was, what the measured value was. In this particular case, we're measuring maybe perhaps a thermocouple or something. And then we automatically calculate the error. And then all of this information is stored in the memory of the 754. So let's say we've chosen to add more points and we're going to do an automated calibration, and this is going to take an hour and a half. You can set this up, confirm it's operating correctly, walk away, and an hour and a half later come back and get all your results from that temperature cal. So there's some significant improvements for just basically the price of a cable if you don't have that. Alrighty, so to top it off, utilizing an expensive serial cable, you can connect your 754 to a dry well or even a microbath from us, and allows you to automate that calibration. If you really wanted to, you can buy a P version of our metrology dry wells, and that allows us to measure a secondary probe. The front panel you might have seen on a previous slide deck, not that one. Yeah, there's one. So this has all of these connections on here. One of the connections on here is for a secondary probe. And what a secondary probe is, it gives you the ability to connect back in and have this device read, again, that even more accuracy, similar to that Callender Van Dusen discussion. It'll be significantly more accurate than the dry well itself, rather than using the sensor. We'll talk about that here shortly in some of the best practices. In fact, right now. Okay, so let's talk about isolating errors, doing that through sourcing of calibrations through dry wells. So one of the key things is to understand the first law of thermodynamics, which states that temperature is going to flow from hot to cold. Now, again, if this is my sensing device that I'm using to control the heaters in the dry well, and say I want to hit 100 degrees Celsius and it's tempting to get this block all to 100 degrees, one of the things we can do is put this secondary reference probe in and make a secondary reference measurement that is closer in point and more accurate, based on the fact that it has more accurate capabilities, to our unit under test. So we run two probes simultaneously and make a comparison measurement. Okay, this in itself is going to give us probably close to a 10-fold more accuracy. We can obviously do all the math for you, but if you need more accuracy, that's what you can do. It also helps us confirm that the dry well and everything has become stable. And then any error in the distance here has been eliminated. Another source of errors is stem conduction. So back to that earlier version where the gentleman had connected in on that big long stem. When you connect a probe into a dry block or a probe into your process, how much stem is exposed? It's basically a heat sink at that point in time. So what it's doing is it's taking the heat out of the dry well and pulling it away. And that process of pulling it away is causing the tip to be slightly colder than the dry well itself. and I say slightly colder. This graph here is a pretty rough example, but the idea is the less immersion we have, okay, the further we go down this line, the greater the error is. So this example is from a 200 millimeter deep well, and we went 50 millimeters out, so about a quarter of the distance out, and that was the accuracies that we had. We pulled it out even further to half of the distance, and the accuracies almost tripled, okay? Inaccuracies, sorry, almost tripled. And again, if we pull it to so that we've only got half, sorry, there's half there, half in and half out, like the significant amount of errors. So people don't recognize this. They don't probably know that it's happening, but if I take like that RTD probe example with that temp stick, on paper it has, you know, beautiful accuracies, but when I put a big long stem conduction on it, I'm basically in many cases not eliminating, but significantly reducing my accuracies based to the standard that's written on the data sheet. Immersion depth. Oh, by the way, a good rule of thumb, getting back to this, a good rule of thumb is that you want at least, no, sorry, less than a quarter of your overall probe length is exposed. Another way to think of that is that whatever the diameter of your probe is, it should be 20 times that is insertion length. So if you have a 1/4 inch probe, that means you should be inserting at least 5 inches into the depth of a well, okay? Now, let's transition that discussion into immersion depth. So if I have a well that's been designed, but it's say a 9-inch deep well and I've only got a 4 or 5 inch probe, when I bottom it out, it's going to be not only resting against that from a heat point of view, but I'm going to be leaving an air gap inside the well. So this air gap itself can create errors, primarily because the dry well sensor readout is here, that's using the controller, and this is the measurement point of my probe. So there's a physical distance there. And this physical distance creates temperature errors. Okay, if you're using thermocouples, again, get back to it. Make sure you use the correct thermocouple wire to make your connection points. When you don't, you create errors. Okay, let's talk quickly about technology in itself. So understand if you have temp guns, just understand your distance of spotting emissivity. We can have a different discussion about that for a different day. Take lab accuracy into the field. These devices are what we call metrology wells. Their accuracy rivals the entry-level stuff at our benches, and they are what we consider portable. They still plug into 120 and they can move them around, and they got a handle to carry them. So take this type of accuracy into the field whenever appropriate and possible. Automate your calibrations. We talked about the cable, do batch testing. And if you want to cover 2 temperatures with one device and don't want to wait, this particular device is interesting. It's not super accurate, but it works great in those 1 degree, 2 degrees Celsius process loops, but it has 2 different wells, one hot and one cold. And the nice thing about them is they will reach their own temperature. There's 2 controllers, one on each side, that tell you the 2 different temperatures. And you put the probe into one, let it stabilize, put the probe in the other, let it stabilize, and you've done your calibration in probably half the time. But the bottom line is if you have any temperature calibrations or any temperature concerns, we have lots of tips and tricks and handouts and, you know, technical knowledge, and come to us and we can help you figure that out. Okay, pulling it all together, I notice we only have a few minutes left for questions, but hopefully the information is coming across clearly on your end. Just pulling it together, just understand that temperature calibrations are valuable. You know, understanding your accuracies and making sure you have the right equipment available to you to not only cover your day-to-day stuff, but those more specialized applications. It's never bad to take a specialized piece of gear to something that doesn't need the accuracy. You're just going to create more what they call guard banding or room to protect you from inaccuracies. Just be engaged with the potential for improvements in your process, not only, you know, accuracies on data sheets, but how you're doing things, the actual process you're going through. And consider the advantages of automating your calibrations and taking all this accuracy into the field. Don't be afraid to ask for help, seek training and further knowledge, which is basically the same thing. But you know, reach out to us. We have lots of knowledge, not only within GTS, but they can call back on us, and between the two of us, we'll definitely help you out. Okay, I think that's it for me. I'm going to toss it back to Chris and take any questions from chat, I guess.
Sounds great. Thank you very much for the presentation, Ken. That was, as you mentioned, lots of information. So folks, we do have 2 to 3 minutes to take as many questions as we possibly can. If we don't get to your questions that you've already put into the queue or you think about it after the fact, please go to our website, globaltestsupply.com. Go to a contact us page to find our contact information, email, chat, phone. One of our technical sales representatives can help you answer any and all questions. So let's take good advantage of having Ken connected with us, and we'll go immediately to, so Tom has a question. So he followed up. So his question is about simulating temperature electrically. Is there some documentation from one of the governing bodies regarding source type calibrations?
We are a part of NCSL, National Standards Labs, and the calibration side of our business might have some documentation to answer your question specifically. I'm not sure exactly what direction the question would take me. If you're looking for traceability, making sure that you have a traceable system, GTS can help you attain that traceability with the equipment you have already. If you're looking for accuracies, there's a bunch of math that goes behind that. Don't just look at the banner specs, but dig into linearity and stability and some of those other discussions. We didn't touch on it here because we really didn't have the time to do some of those math discussions, but if you're simulating into a transmitter, typically you want to be, 4 times more accurate than maybe the transmitter as a part of your calibration, but it really comes down to loop accuracy. What am I comfortable with the overall loop accuracy? And if I can simulate an RTD value into that system, that's going to be 4 to 10 times more accurate than my total satisfaction for the loop, then every little component along the way adds in accuracy using root sum square. So, but as to getting back, is there any governing body? I don't think anybody's going to come out and say that you have to do it a certain way in terms of simulating versus sourcing or anything like that. I think just trying to think if I'm covering the answer, but you know what, if we didn't cover your answer, Tom, feel free to reach out to us. Maybe we can add some more detail beyond typing on a chat window and have a discussion. I'm more than happy to do that with you.
Perfect, thank you, Ken. Definitely, and just to follow up to Ken's point, Tom or anyone else, if you do have a question that we didn't get to today, or you want a little bit more clarification, go to our website, globaltestsupply.com, find our contact information, reach out to us that way so that we can follow up with you and answer your question there. William had a question. We'll take one last one so we can respect everyone's time. Something along the same lines. Is there a national standard for temperature to reference, such as the ASME B40 for pressure?
Okay, so I heard the word pressure. We have a pressure standards presentation coming up in, 3 or 4 weeks now? We're actually building it out right now. So when it comes to that particular answer to the question, I will actually just take that offline with you, Chris, if that's okay. And maybe we have a way to answer both Tom and William's questions, because they both seem to be standards related. So if we can go from that avenue, I'd be fine with that, if they're okay with that as well.
I think that should be all right. So both of you, we will take your contact information and we'll contact you offline to answer your question more specifically. As I mentioned just a couple minutes ago, we do want to respect your time. Dawn, just very quickly, your question about the presentation. A recording of the presentation will be sent to you in the next coming days. It'll also be available on our YouTube page as well, so you can reference that. And I will take the opportunity to thank Ken very much once again for the presentation. Lots of information, lots of topics covered. I do hope that everyone did find it informative as much as I did. So Ken, thank you very much.
You're welcome. Thank you, folks. Thanks for taking your time. It's all valuable and we appreciate it.
So on behalf of Global Test Supply University, we thank you very much for attending our webinar today. We hope you found it, as mentioned, informative and helpful. Global Test Supply, we are here to assist you in any way. Visit our website, globaltestsupply.com, for anything you need. Through our website, you can find our entire list of Fluke products, as well as technical specifications, data sheets, manuals, descriptions, pricing, availability, look at our rental section as well, along with all the contact information for us so that you can get in touch with our technical support staff for any and all questions that you may have. At the end of this webinar, in a couple short minutes, you'll be asked to complete a very short survey. Your feedback is important to us and will assist us with improving our webinars, as well as bringing you more topics that are of interest to you. As Ken mentioned, we do have a few webinars coming up over the next few weeks and months. In the training section of globaltestsupply.com, you can find our full schedule of upcoming webinars, including dates and topics. Don't forget that as a thank you for attending today's webinar, your name will be entered into a draw to win $100 towards your next online order. The winner will be announced on our social media channels, so please be sure to check us out there. Ken, once again, thank you very much, and thank you all for attending today. We wish you a great rest of the day.
Cheers. Thank you. Bye.